Hi, folks. Some of you may be here early. Go ahead and enter your names so I can keep an accurate roster. Hey, Mason, how are you? Hi, Madison. Good to see you. Speaking kind of interesting. I can't see you at all. Okay, Mason. Hi, Shaniqua. Shaniqua, what was the last thing we talked about in terms of the muscle contraction? Hi, Sonia. Hey, Elizabeth. How about it, Shaniqua? What was the last thing we covered in terms of muscle contraction? Michael Burrows, Malibu Mizzy, huh? Oh, nice to have you back. Haven't seen you for a while. Shaniqua, is that on page 357? Hi, Cameron. Hey, Tamika. Thank you, Madison. Hi, Jason. Did you ever get a hold of Rodney? Hey, Madison. Hey, Courtney. Good afternoon, Morgan. Hi, James. Hope all of you are staying pretty well. I want to come down with that stuff that's going around. Oh, there she is, the real goddess. Good to see you, Kira. Hi, Stephanie. Courtney, so far, things are going well. Nobody's coming down with the stuff yet. We try to keep our distances, not so much in the home because we've been living with each other anyway, but get with other groups, we try to stay, or other people, we try to stay about 6 feet from them. Good, Madison. Yes, I did, Sonia. I sure did. Okay, Antonia. Let's see, where are you? Destiny. Glad you're here. Tamika Johnson, alive and well. Thanks for asking, Courtney. Yeah. Hey, Katie. Hi, Ann Grace. Well, I appreciate your compliment to some degree there. Uh, I've got plenty to do, I can tell you that. But if you have a couple of questions, you could call me. Maybe we could talk it over the phone for, maybe I could say it in some way so that you understand it. That's why Malachowski teaches micro and I teach micro. We don't say it the same way. So sometimes he says it and people understand it. Sometimes I say it and people understand it. That's why it's good to have different teachers sometimes. But you can call me if you want to. I'll be around this afternoon. Okay, everybody in section 6 seems to be here. Okay, so we're missing Megan and Brandon and Nani and Valerie and Shay. Everybody else is here. Okay, let's go over this structure of the muscle and contraction quickly, and then we'll move on to some new material. So let's go back to page 343 just to get the picture in your head about a muscle fiber. So I'm on page 343. I'm at figure 10.4, 10.4. So just look at the structure. Get a picture of the structure. You see the, over to the right, you see the myofibrils, composed of many, many sarcomeres, thousands of sarcomeres. And you see the sarcoplasmic reticulum. You see the transverse tubule. So somebody asked about all the little pipes between the terminal cisternae. That's still sarcoplasmic reticulum. But in those terminal cisternae, what ion is contained? What ion is contained in the terminal cisternae? Title of the figure is Structure of a Skeletal Muscle Fiber. 10.4. In my book, it's on page 343. You got a different edition, you might find it on a page or two over one way or the other. Anybody going to try to answer what ion is found in the terminal cisternae? That's right. Very good, Madison. Very good, Elizabeth. It's calcium. Okay, so you got that picture about the transverse tubule and the two terminal cisternae. You look down at the little box and you got the triad. You can see those little tubes are open. They just for the picture, but they normally continue with other terminal cisternae all down the course of the myofibril. That's correct, Destiny. That's correct, Sonia. So you got to drink your milk, don't you? Got to get some calcium in there. Eat some cheese, eat some ice cream, eat some yogurt, things like that. We need that calcium. Okay, again, look on page 344. This is 10.5. The figure is 10.5, structure of the myofilaments. And as you look at that little muscle fiber midway on that page, and you see the enlargement that they're making, they're looking at the myofibril, and then they show you the proteins that compose a sarcomere. Now remember, we typically think only of the myosin and the actin, but you've got other proteins that are necessary to stabilize those filaments. They're all part of the structure, the healthy structure of the sarcomere, which is the contractile unit of a muscle. So as you look at the enlarged myofibril, where you can see the little Z line, that's a different protein. You can see the actin, that little skinny purple filament, that's one. You see myosin, which has a bunch of heads on it on either end. Thicker filament. You see the M line, the 3 lines going down the middle, that's a particular protein. And you notice that on the Z lines, which is a particular protein, there's that coil. They called it elastic filament. We called it what? What did we name that protein? Or rather, somebody else named it. We're just learning it. What's the name of that little coiled spring-like structure? We know it's a protein. It's got a particular name. Starts with a T. That's correct. Good. Very good, ladies. Very good. So that's 1, 2, 3, 4, 5 proteins in the sarcomere. And then you look over to the right and you see the thin actin filament. The thin filament's got those little purple balls. They look like little grapes, dark grapes instead of the green grapes. Some people call them red grapes. But each one of those is a little protein, and you can see they're all connected to each other. And then you look at the blue line, and that's tropomyosin. That's another protein that we have to have. The tropomyosin covers the active site of the actin molecules. That's what keeps your muscles relaxed. And then you see the little yellow structures. It looks like 3 little balls stuck together. That's troponin. And you remember troponin actually moves the tropomyosin whenever we're contracting. We're going to go through that quickly in just a second. Any question about that so far? So we've got about 7 proteins there. We think of only actin and myosin, but the others got to be there. We don't have that, then everything's just a mush. It's kind of interesting when you think about it. When you eat chicken, when you eat beef, when you eat pork loin or whatever, barbecue, what you're doing is you're eating the myosin and the actin and the tropomyosin and the troponin and the titin and whatever the M line is. They just call it an M line right now. They probably have some fancy name for it. But when you eat that, that's what you're eating. You're actually, when you cook that, then you tend to break apart those proteins, you denature them, and so it makes it easy for us to chew them. We throw some good sauce in there, and that's how we get our protein. Not the only way, But that's what we're doing when we're eating that. So let's go over a number of pages. Look over to 348, figure 10.9. Says the I band and H zone, that's the title of it. Well, it's been figure 10.9, the sliding filament mechanism. Changes in the band of the sarcomere during contraction. Just trying to get you to picture it. So you look at the top and you see a relaxed sarcomere on page 348, figure 10.9. And you see the actin filaments, those very slender little purple filaments that are hooked to the Z line. That's part of the I band. And they just barely get between myosin filaments at that point. But when contraction occurs, look what happens. The Z lines get closer to each other. The myosin pulls the actin in toward the M line. So the sarcomere contracts during contraction. That A band gets smaller. Okay? So does the I band, actually. And it's actually the I band that gets smaller. Now let's scoot over to page 352. And we're looking at the process of skeletal muscle contraction and relaxation. Come down that first column, you see the term neuromuscular junction. What is another term for that structure? Another term for the neuromuscular junction. What do you think, Katie? What's another name for that? That's correct, Courtney. That's correct. Madison, that's right. Mm-hmm. You guys are spelling it correctly, too. That's great. Did you get that, Katie? Stephanie, you're right. So look at the look at the picture to the right. You're looking at the myoneural junction. You see it up top. There comes a motor neuron. Look at that little illustration of the muscle fiber. And you see the motor neuron coming to it. You got three little divisions. Got to be quick, don't you, Katie? Losing those fingers up. But you're correct. Okay, you got the motor neuron, you got the little splitting off. We'll talk about those later in the next chapter when we get into the nervous system. They're called telodendria. You don't have to know them at this point. But they attach to the muscle fiber, and you see the little block on there. That's a picture of the myoneural junction. That's a little isolation of it. Now look down there and you see that enlarged picture of the myoneural junction. Now notice you still got the sarcoplasmic reticulum in that little muscle fiber up top. And you can see the triads. You can see the kind of beige transverse tubules, and on either side of that, you've got a terminal cisterna, or I just call it a terminal cistern. That's probably cisterna since it's Latin. So we see the axon terminal. That's that bulbous structure. Inside, you got the synaptic vesicle. What does that synaptic vesicle consist of? Now, I'm not asking what's in it. That's acetylcholine. of what is the vesicle composed of? Of what is that vesicle composed? Good question, huh? Having a hard time figuring the answer out? Courtney, got the term. That's correct. A lot of those organelles are made of, that's it. That's right, Destiny. Katie, you're correct. There you go. Good. That sure is going to make my life easier when I ask questions like that. I really enjoy seeing y'all succeed, but I got to make you work. Madison Becker, it's got protein in it. That's correct. It's got transmembrane proteins in there. Basically, we'd say it's a phospholipid bilayer, and then you do have proteins in there. That's right, Shaniqua. You're correct. So when you look down there at the myoneural junction, the enlargement of it, you see the axon terminal, you see the vesicles inside, you see the little diamonds, which are the acetylcholine, come down to where you see the sarcolemma on the left, and then you look as you move to the right in that space, that's called a cleft. What is a cleft? That's correct, Jason. That's correct. What is a cleft? It's an opening. Good. Remember, Moses was pushed into the cleft of the rock. There's a song called Rock of Ages, Cleft for Me. Some kids are born with a cleft palate. That means the roof of their mouth doesn't seal, so there's an opening there, a space. That's right. Good. Very good, ladies. Very good. And in that cleft is extracellular fluid with sodium ions in it. The sodium ions are floating around in the extracellular fluid. Got to have your salt. If you like your salt on your French fries or whatever, my wife puts salt on everything. She just has that taste for that. I don't have that taste. She does. I like pepper. Now, you see that sarcolemma off to the left, follow it down, and you see that little ACH receptor? That's an acetylcholine receptor. That is a transmembrane protein. It is a gate to get in or out of the cell. It's a particular protein. That's because it's got different amino acids, different numbers of amino acids, different sequences of amino acids, and we end up with a different protein that functions in a particular way. You can't just throw amino acids together and get something. It's got to be done just like our words. They've got to be, Michaela, great. I'm glad you got on. New experience. Good for you. Let's see here. Okay, Sonia is saying, what figure number is that? That's figure number 10.12. 10.12 in the textbook. It's in my book, it's on page 352. I've got the girl doing the track on the front. They don't tell you what the addition is, but some of you might have it where the guy's hanging off the cliff. Boy, that'd be something to climb like that. Whew. Gives me chills thinking about that. That's a good question. I don't have that drawn up. 1014 in the older book, 10.14. Anybody looking at the e-text or anything like that? E-text, it's 1014, Cameron. Okay, so we've got it set up. We're looking at 1012, 1014, whichever one shows you that myoneural junction. So the structure's there. Let's move over to the next picture, which is 10, in my case, 1013, maybe it's 1015 in some of your books. And you see the axon terminal, you see the vesicles inside, and you see the sarcolemma and so forth, and little transmembrane proteins. You're welcome there. Welcome, Cameron. So here we come. We want to move our legs. So this action potential, as you see up at the top, that green arrow coming down the axon to the terminal, you can call that a nerve impulse. It's an electrochemical message. There's several different things that, good, Sonia, I'm glad to see it. But it's really a swapping of charges. That's where sodium and potassium are moving, and that is the message that comes down that axon to the axon terminal. Now, when that nerve impulse gets to the terminal, look what it does to the acetylcholine synaptic vesicle. You see the synaptic vesicle fuses with the cell membrane of the neuron. Remember, that's all phospholipid bilayer. So it's no big deal. That little vesicle just slides right in there and opens up, and out comes the acetylcholine. That's the little diamonds. And the little diamonds attach to the transmembrane protein. When they attach, those proteins, which are gates, they're doors to the inside, or depending on where you are, the outside of the cell, those doors open and sodium rushes in. Sodium rushes into the cytoplasm or the cytosol of the cell. And remember, we said there was a lot more sodium outside the cell than there is inside the cell, but that's changing now. Why does the sodium move from the synaptic cleft through the gate and into the cytosol? What causes it to do that? Sodium is not alive like you and I are, but it conforms to some physical and chemical laws. So why does the sodium move from the synaptic cleft into the cytosol or the cytoplasm of the muscle cell? That's correct. Malibu Mizzy TV. I don't know who that is. I don't have that listed in my grade book. There's no Malibu Mizzy. Diffusion is what's happening. You're correct. What's the definition of diffusion? You got it, Stephanie. That's it. Think about what the definition of diffusion is. That's right, Madison. That's right, Atlanta Grace. That's where the Atlanta Grace, that exocytosis is where the synaptic vesicle fuses with the cell membrane and empties the acetylcholine. That's got to happen before sodium rushes through those transmembrane proteins. That's right, Malibu Mizzy. High to low concentration. So there's a high concentration of sodium in the cleft, low concentration in the cytoplasm of the muscle cell, moves from high to low. You're correct. Diffusion, you're correct, Sonia. So now we've got sodium moving inside. Flip the page. Look on, I'm going on 1014. You might be on 1016 or something like that. Good, Anna Grace. Good. So as you look at 1014, again, you see the sodium coming through those protein channels and follow it to the right. You see all those positives. So that's the action impulse, that electrical movement of ions where the inside becomes positive and the outside becomes negative, as opposed to what it was before that. It was positive on the outside, negative on the inside. So you see the positives go all the way to the right, and then they dive down the T-tubule. So that impulse, that action potential, is moving through the T-tubule. And as it moves through the T-tubule, on either side, the terminal cisterna release their calcium. They let it go. They let calcium go into the cytosol or cytoplasm. So as you look at the terminal cisternae on the right, you can see right about the middle of it, it says calcium channel. So they've got channels. Proteins, again, different kinds of proteins, thousands of kinds that we use and need. But the gates for the calcium are different from the gates of the transmembrane protein. Sodium comes in to the cytosol, you're right, Sonia, and when an impulse gets to the terminal cisterna, via the T-tubule, calcium comes out. That's right. Calcium comes out into the cytosol. So you're correct in saying sodium out, sodium in, calcium comes out. Okay, now let's look on the next page, figure 1015 for me. 10.15 might be 1016 or 17 for you. Now, as you look at the picture, it says underneath there, that little box, go down to the small box, and you see it says at rest, tropomyosin blocks active sites. That depolarization, Destiny, is another way of saying that exchange of ions. So whereas the muscle fiber on the inside was negative and was positive on the outside, that has changed. That's depolarization. That's another way of describing the movement of ions so that you get a reversal of charges. I'm not going to ask you that, but that's what's happening. Okay, so you got that picture down at the bottom of page 355 and figure 1015. Now go to the right. You don't want to say that, Jason. You don't want to say so sodium changes to calcium once it goes through the triad. That's not true. That's not true. Sodium always remains the same thing. It's still sodium. And calcium always remains calcium. You're just dealing with two different ions. So you've got to have some salt in your diet. You've got to have calcium in your diet. So don't get them confused like that. Good, Destiny. Okay, so we're in that little block down at the bottom. You can see tropomyosin blocking the active sites. If you look really closely, you can see there are little tiny holes under that blue protein. Of course, they did all this color for you and me. Proteins don't come necessarily in colors. Chemical makeup doesn't change. Still all protein, still calcium, still sodium, and so forth. Phospholipid bilayers, that's all that. We're just talking about the movement of ions. So as you look at that little square down at the bottom where it says at rest, tropomyosin blocks actin's active sites. Now move to your right, and you see on the troponin 2 little green balls. And the green balls represent calcium. But notice what has happened when 2 calcium ions attach to the troponin. Look at the tropomyosin. It has moved so that the active sites of actin are available to be attached to the myosin. That troponin protein, when it was connected with 2 calcium ions, moves, changes its shape, and it moves the tropomyosin off. I mean, it might be a 1/1000th of a meter. It just moves, but that's enough to open the active site up. So it's like exposing the keyhole that you want to put the key in. Sometimes you may see locks like that, and they have something that swings in front of the keyhole. And what's happened is that tropomyosin has moved, so the active site, the keyhole, so to speak, is open now, and the myosin attaches. And now we're over on page 357. We're on figure 1016. Takes up the whole left-hand side of the page. So the active sites have been exposed. You don't expose them, you don't get any contraction. Because the myosin's got a hook to that particular place. It doesn't happen on the other parts of the actin, only that place. Just beautiful. I am glad you mentioned that, Destiny. I looked at that on the e-text, and I think you're right. It does give you a motion type thing. And so look at that, because I'm going to ask you this stuff, and you want to be able to explain it to me. Thank you, Destiny, for doing that. So we're on page 357. We look at the top, and you see the relaxed sarcomere. And you see that the myosin is the red sticks in there, and then the actin is the little thin ones, and they're about halfway in. So you look down there at the first rectangle, you see a myosin on either side of the M line. A couple of myosins have hooked to the first actin protein. You come down to the next block, and you see the myosin is contracting. It is a contractile protein. It's not a protein that's going to digest anything. Its purpose is to move. And so it pulls the actin to which it is attached toward the M line. Now we're in literal contraction. And then you look at the next one, the next block, and you see that myosin head is attached to number 2. Now remember, the myosin has a lot of heads on it, so they're just showing you one head. But all those little bulbous structures on the end of the myosin filament, they attach to a number of these active sites. and they pull the actin in towards the middle, toward the end line. Destiny says, look at 1018. Figure 1018. That helps you. That's great. Thank you, Destiny. And you see down at the bottom, back on 357, the actin's been pulled in. The sarcomere has shortened. The distance between the two Z lines or Z discs has gotten shorter. That's what's a contraction. Whenever a myofibril is going to contract, let's say the myofibril of that muscle cell has 35,000 sarcomeres, all 35,000 shorten like that. One muscle fiber will contract all the way, doesn't contract part of the way. So, you now know about muscle contraction, about relaxation. Look on page 358. And you should see a section of or column that has muscle relaxation for its heading. So now the muscle is going to relax. We're going to check off 3 of these events. You see in number 1, it says acetylcholinesterase. Now, if you see ASE on the end of a word, what does that tell you? It tells you actually 2 things. No, Madison's not sugar or sugar. Something else. Sugar is a carbohydrate. Madison Oaks says it's an enzyme. That's correct. Anytime you see ASE, think enzyme. And for us, as far as we're concerned, any enzyme is a protein. Good. That's right. We're looking at the process of muscle relaxation, Anna Grace. Title of the figure? It has no figure. Let's see. Well, it does have a figure on page 359, figure 1017. Figure 1017. So as you look at that picture on 1017, look over to the left where the bineural junction is located, and locate the little blue ball. Tiny little blue ball there. It says ACH, and then down below it has the big word acetylcholinesterase. Acetylcholinesterase breaks down acetylcholine. Thanks, Tamika. Look at number 3. Calcium ions are pumped back into the sarcoplasmic reticulum. Now, if you look at the illustration, 1017, Anna, like you wanted to see that. Look at the terminal cisternae on either side, didn't make any difference. But you see the little black arrows by the calcium channels? You see how the little arrows are going from the pink cytosol into the blue reticulum. And the little green balls are the calcium ions. So the calcium ions were released into the cytosol. Now we have a pump that pumps them back into the terminal cisternae. So they rush out, rush back in, rush out, rush back in. Sounds plumb cumbersome, doesn't it? Now, while we're talking about ions, look at your axon terminal and look to the right along the sarcolemma. You see how the positive is back on the outside and the negative is on the inside. I'm not going to ask you all that, okay? I'm not going to ask you that. But you want to remember that the calcium ions are pumped back in to the cisternae. That takes energy to do that. Yeah, you're hitting on to that, Sonia. That's right. When we get into the nervous system, we're going to be talking about that sodium-potassium pump. Not the easiest thing in the world to understand. I did say that, Stephanie. You're correct. And Shanika, you're correct. The sodium-potassium pump is responsible for that. So acetylcholinesterase destroys the acetylcholine, breaks it up. Calcium ions are pumped back into the terminal cisternae. Look down at the bottom of that figure, 1017, or I think Tamika said it was 1019 in the e-text. That's fine. Look at the bottom, that little rectangle down at the bottom, and you see, look at the little white arrows. Tropomyosin moves back into the position of blocking the active site. And troponin has lost the calcium ions. Everything's back like it was before the contraction. So troponin and tropomyosin block the active sites. The muscle relaxes. Seems so cumbersome, doesn't it? But you know it just happens like that. And it does it over and over again. Think about you coming up the stairs. Some of you might have taken the elevator, some of you took the stairs, but every time you took a step, you lifted that thigh and that lower leg, and you placed it on the tread of the step. And all this is going on, back and forth, back and forth, back and forth, so quickly, using a lot of energy. That's how you lose weight. You got to get some exercise. Don't eat as much, and you'll be burning off energy, because it takes energy to get all this going. Now, there's one thing I want you to look at. I think we'll be through with the contraction. I want you to go back to page 346 is okay, or you can look at 344, either one. That's where we saw the coil, that protein called titin. Now it looks like a little spring. Now consider, as you look at the A band, and you see the myosin, look at the tip of the myosin molecules. There are two of them on there. I'm on 346. And you see extending, or attached to, I guess you could say, that bulbous, all those little bulbs on there. You can see that coiled protein. Now remember, when the sarcomere contracts, what happens to the Z lines? Somebody tell me, what happens to the Z lines, those Z discs, during contraction? They shorten. That's right. They get closer together, don't they? So what's that going to do to that little spring-like tighten? Pull closer to each other. That's right. Pull closer to the M line. You're correct. Shorten. So what happens to that elastic filament? What happens to that tighten that looks like a spring? That's right, Destiny. They get shorter. They get shorter. That's right. They're compressed. Now that happens on your car. You got 4 wheels on your car, two up front, 2 up back. And when you hit a bump on the right-hand side, it doesn't just throw the whole car up. What happens is you got an arm there, it's got on a spring, and it'll move, but this one won't move. So just that tire pops up, and then it comes back down once you're over the bump. Compressed. That's a good word, Sonia. It gets compressed. That's exactly right. And Jason says the springs come together and then they push back when it's over with. That's exactly right. So relaxation means that elastic filament, which is called tighten, pushes back so that the Z lines are in the original position before stimulation. Yeah, it's kind of like slinky. That's right. That's a coil. That's some type of a coil, isn't it? Now that slinky, you just pull it apart and it comes back. But they make springs that have a lot of space between them. You know how a slinky can just stack on top of each other? But they'll make springs where those springs are, in terms of the windings, they're apart. So if that tire hits a bump and pushes up, that spring tends to push back down. That's what's happening with the tighten and the Z lines. It pushes back. That's an amazing stuff, isn't it? Just flat out amazing. You can see you could give your life to studying all this stuff about muscle contraction. There's a lot more to understand. Okay, let's go over to page 361, at least in my book. The heading that you're looking for is 10.5. 10.5, it says energy sources for skeletal muscles. Under that heading of energy sources for skeletal muscle, 10.5, there's a paragraph that says immediate sources of energy for muscle contraction. You want to read that paragraph. It talks about ATP, adenosine triphosphate. And you're going to read about a new substance called creatine phosphate. So it's involved in combining with, as you see the formula down below, ADP stands for adenosine diphosphate. See, creatine's got a phosphate on it. That's what we need. So creatine phosphate adds, as you see in that formula, one of its a phosphate group to the ADP. You get ATP, which is adenosine triphosphate, and creatine's left over. So that's some quick energy for us there. I can help you run 100 meters when you need to. Used to be able to do that, but I don't know that I'd even make it now. Somebody's looking at the ebook. I think Destiny, you were. Got an answer for Sonia there. Looking for immediate sources of energy for muscle contraction. Sonia, she says 361. You see that? Now you're looking at 10.5, if I remember correctly. I think that was what we were looking at. Yeah. So we want to go to 10.7. 10.7. You're going to see it says muscle tension at the organ level. My book says 368. And you can help out there with Destiny. You can help out with whatever number you've got there, where you see that heading 10.7, muscle tension at the organ level. Jason says 368 in the older book. That's where I am. 364 in the e-text. Thank you, Tamika. I keep picturing you guys in my mind. Tamika's right in front of Sonia and Destiny's on. Nobody's behind Destiny or in front of her. You guys are big help. That's great. Thank you so much. All right, so you look at muscle tension at the organ level, and you come down to this heading that says motor units. Motor units. And you want to come down to the second line, and you see it says a single motor neuron along with its muscle fibers, which it innervates, should have a little word which in there, is called a motor unit. A single motor neuron, that's one cell, along with the muscle fibers it innervates, is called a motor unit. I want to know that. Got a lot of motor units in our body. Go to the next paragraph. An average motor neuron, a motor unit, consists or is made of about 150 muscle fibers for that one neuron. That's the average. Okay, thank you, Tamika. Appreciate that. Page 368 in the e-text. I wish we could kind of have a double screen and you could look at it on yours. That'd be great. But I ain't got it here that I know of. Don't have the program for it. Or I don't know how to do it. Now look at that statement down there in the second paragraph. That's right, 150 motor, no, not 150 motor neurons, okay? One neuron connected to 150 muscle fibers or muscle cells, okay? That's a motor unit. One neuron, and in the average, it splits 150 times so it can connect to 150 muscle cells. Destiny, let's see. Do you see the heading says paragraph? And in the first, oh, that's crazy. I'm getting goofy here. You see the heading says motor units. And the paragraph right under motor units gives you a definition there for a motor unit. The number we're talking about is in the second paragraph, the last two lines of that second column on page 368. An average motor unit consists of 150 muscle fibers. One neuron, 150 fibers. 150 muscle cells innervated by that one axon or one neuron. And you see it says the number can vary widely with the degree of motor control needed for the muscles. Got it. Okay, good, Destiny. Now, keep reading. You're over on the next page, 369. It says muscles that require fine control, like writing. Good, okay. Stephanie, I think I'd change that to say a single motor neuron, let's see, equals the motor unit equals 150 fibers. You'd want to say something like single motor neuron plus 150 muscle fibers equals a motor unit. Okay, so now we're looking at this next sentence. Muscles that require fine control, such as those around the larynx or in the fingers, like your writing, will have multiple small motor units, often containing as few as 10 muscle fibers per unit. Think of what you can do with your fingers, how some of you may be able to play an instrument, play a piano. Left hand is holding down on a guitar, or hold the strings on the frets, and the right hand could be picking different strings. Got to have a lot of control in your fingers. How about your lips and your tongue? Think of all the words that we have to say and how we have to form our lips and move our tongue at the same time. So you can imagine the tongue and the lips are highly innervated, 10, 15 muscles per motor neuron. We're going to get to tension in just a couple of minutes, so hang tight. So this is how we control our fingers so well. We've trained them. But also you can think of it in this way. That's correct, Stephanie James. That's correct. You take this pencil or this pen, and I pick it up with my right hand, and I'm using my deltoid up here to lift this. So what I'm doing is contracting, let's say, 150 muscle fibers. But suppose I had a brick here, which might weigh a pound. I would have to have more muscle fibers contract in order to pick that brick up. So you see, we learn in our minds something has a certain amount of mass, has a certain amount of weight, and we know that it's going to take a little more to pick that brick up than it does to pick up that pin. So we use more muscle fibers, more motor units to get the job done. You use a lot of units, motor units, when you come walking up the stairs. If you're one of those who walk up the stairs as opposed to taking the elevator, you activate quite a number of motor units because you're picking your weight up every step. Got the picture? So when we pick something up, we don't pick up all the muscle. We don't use all the muscle fibers because we don't have to. We just use the one that's necessary. And we have learned that we need to put more pressure on that brick than we do on this pin. Can you imagine picking up this pin and contracting all the muscle fibers that you would contract to pick a brick up? You go. We don't want to do that, do we? No, we don't want to do that. Okay, so now you know how what a motor unit is and how we use multiple motor units when we have a heavy object to lift, one or two motor units when we have to pick up something that's very light. I'm not sure what that means there, Stephanie. Using the knees to lift. Oh, versus your back. Yeah, that's a good thought there. Okay. I see verse like a verse in the Bible, but it's versus, VERSUS. But you're on the right track. You're thinking the right thing. Okay. Now, Sonia, we finally get to your muscle tone. So you look in the column next to that diagram, figure 1025, and you see muscle tone. So what I want you to do is come down 3 lines where you see the heading muscle tone, 3 lines. It says even when a muscle is at rest, it still has some degree of tension. It's not flaccid. It's not flaccid. It still has some degree of tension. That's muscle tone. Now you don't want too much, you don't want too little. This is another one of these homeostasis type things. So look in the next paragraph. If the tone in the skeletal muscle is abnormally low, you have a condition, as you see in the bold print term, hypotonia. Hypotonia. That means the muscle is moving toward being flaccid or completely relaxed. No sarcomeres are in there holding just a little bit of tension. You come down below hypotonia, you see hypertonia, and that's where you have too much tension and the muscle can knot up. KNOT. It can knot up. And it feels very firm. Sometimes it can be very painful. Okay, now we're not going to finish this chapter today. We're going to do it on Tuesday of next week. But go to the next couple of pages, look for 10.8 and see skeletal muscle performance. Section 10.8 and look for skeletal muscle performance. I don't know about that, Sonia. I'd have to chew on that a little bit, but I won't ask you any questions about it, okay? You do want to be active, though. It's good for you. Okay, under skeletal muscle performance, I'm on page 371. Second column, look down at the heading called resistance training. Now, all of you have probably noticed that even girls can enlarge their muscles. Guys get bigger muscles from working with weights or whatever. But you see the word, the bold print term, hypertrophy. Hypertrophy. Hyper meaning greater. Trophy talking about growth. Look over on the next page, 372, figure 1027. Figure 1027. Look at the muscle fiber with normal use. That's one fiber, okay? And how many myofibrils do you have in that one muscle fiber? You see the cut face, count them. How many do we have? Jason says 8. Anybody agree with him? Mm. 10.28 if you're looking in the e-text. Thank you, Anna. Okay. Anna says 8. Madison says 8. Destiny 8. Good. Okay, you're all counting the same. Now, you start, if that's a biceps, and you start picking up 5-pound weights, and then you move to 8-pound and 10-pound and so forth, here's what's going to happen. Come down the middle arrow that goes sort of off as an angle to the right, and then it moves over to where it says resistant training. Now look at the number of myofibrils in that muscle. How many do you have? That's right. You get 12, don't you? So your muscle is able to produce additional myofibrils to increase your strength. And so the muscle becomes larger and stronger. That's hypertrophy. That's hypertrophy. That's why when you work out with some weights and you're picking up heavier and heavier, up to a point, your muscles get bigger, they get firmer. It's good to have some strength. Even at my age, it's good to have some strength. Although things don't work as well as they used to, it's still good to have what little strength you can come up with. Shay, you came in. That's great, Shay. I can count your present today now. So that's how muscles get bigger when you work out. Now, that's not all the whole answer of working out, whether it's walking or hiking or something like that. We're not going to get into all of that. So the last thing we need to look at is, and we're out of time. We just got a page and a half here, but we'll pick that up on Tuesday. You see over on 10.9, talks about visceral muscle. Remember, that's in your organs inside, visceral and cardiac muscle. We'll talk a little bit about those, and that'll be the end of this chapter. And so from there, we'll move into the nervous system. And that will be the fourth test, muscles and nervous system. Plum taxing, isn't it? Do you have any questions? Thank you for letting me hold you over for 3 minutes. But I think it seemed like I was letting you out 3 or 4, 5 minutes, kind of laughingly saying, would you like to get out of here early? You guys rolled your eyes a couple of times. Any questions? Okay, I guess nobody's got any questions. Keep your hands away from your face. 6 feet from people. Obviously, I don't stay 6 feet from my wife, but we're living in the same house. But somebody else comes in, we try to stay some distance from them. Let's see if we can let this virus dry up and blow away. All right, you have a nice weekend. Lord willing, I'll see you on Tuesday. Bye.